This week we're going to talk about networks, and the diagram here is a very complex network that I've used in my research, and we're going to get back to looking at that later. The objectives for this lecture are to introduce the network approach, which again is one of the 5 approaches we're going to use to gather information and help understand problems. And then I'm going to describe several examples. One is going to be a food web, and the other is going to be a more spatial habitat fragmentation type use of the network approach. And then we're going to go through several examples of these, and then we're going to talk about the relationships of the pattern and systems approaches to network. Now, the network approach really focuses on connections, and you can use this to describe any relationship you want. So in a systems view, which we talked about last lecture, the stock and flow systems, you're really constrained to looking at energy or material flow, and every particular link you make as a stock with flow between it has to be of the same stuff. Now, in a network view, you can represent that, but you can that material and energy flow. You can also represent other relationships between organisms or nodes of the network. So in this diagram here, this nice diagram of a cartoon of a forest, you can see that the blue jay might be actually eating the fir cones, and in the process they get energy and material, but also the uneaten seeds that either pass through the blue jay or drop on the ground are going to be part of how the seeds are spread. And so the blue jay plays a role in the ecology of the tree by distributing the seeds. Similarly, you see in the background there's a moose having a little discussion with several wolves. Well, in a stock and flow systems diagram, we'd only be interested in energy and material. It's sort of in a simple model, but even in a simple network model, we could describe how the presence of wolves changes the behavior of the moose, and how the moose herd activities is detrimental or positive for wolf predation. So we can describe those, and it's fully legitimate to put those into a network approach, because we're really trying to get at what are all sorts of relationships. Now today we're going to talk about 2 versions. One's a node and arrow, very similar to this forest cartoon here. Another is a spatial grid. So the two examples, a food web, we would represent with nodes and arrows connecting those. And the example I'm going to develop here in just a second is where we have the grasses, here represented as 3 species of grass, G1, G2, G3, and the herbivores that eat those, and the predators that eat those herbivores. So we're going to develop a little network and what that means. And for a spatial grid, we're going to talk about several spatial grids. We're going to talk about habitat fragmentation, but other examples in the reading and in the videos talk about forest fires. And here's just an image of the output of a simulation on a spatial grid, where the white areas are just freshly opened up space. The light green are plants just starting to grow. As they get darker green, shows more and more tree density, that is more and more fuel density. And then where it's black, it's just recently burned by a lightning strike. So the output of this model is that it develops it shows how a landscape develops a mosaic of all these different age classes of plants and open areas due to occasional light strikes. So let's look at the node and arrow diagram of a food web. And in this case, I want to start with you imagining that the linkages between the grass and the herbivore and the predators are more like springs. That is, there's a little elasticity in it. Instead of it being a pipe that carries energy and material, it's more like a spring. And the relationship between, say, grass 1 and herbivore 1 is one of the grass provides food for the herbivore, but the herbivore reduces the amount of grass that's there by eating it. So it's a two-way relationship when you describe it that way. So let's visualize what happens if grass 1 is perturbed. And in this example, I've sort of stretched out that link and made it thinner because it's as if grass 1 is less available. What happens? So the linkage between grass 1 and herbivore is stressed because there's less grass. Well, what I'm trying to represent with this diagram is that the rest of the network compensates for that. So the relationship between grass 1 and herbivore 1 reaches a new state because there's going to maybe few herbivore 1s and a little bit more grass 1. As there's less herbivores, the grass is going to grow back. That helps reestablish that. Herbivore 1 might have a stronger linkage to what it's doing by eating stuff that's in grass 2, and then the rest of the neighborhood, the rest of the network also sort of shifts. And this is a very important feature that we can capture in a node and arrow diagram, which is this idea of a compensatory response of the overall network. Every organism in this network is shifting a little bit. So you might want to make this more concrete for yourself by thinking that herbivore 1 is a rabbit and grass 1 is one of the grasses that it eats. As that grass 1 becomes rare, there's less rabbits, but then the rabbits that are there shift over to eating another sort of grass, and that the number of rabbits and what they're eating propagates. That effect propagates through the overall network. So this is a very important feature of compensation of the whole network to respond to a stress. Now, shifting to a spatial grid network, and this is we're going to be looking at these types in class where we're looking at habitat fragmentation in the laboratory. This is part of what you're looking at. So in the top grid there's a lot of green space, and then there's spaces where the natural habitat has been removed for human development, for example. And as you have a small amount of human development, there's still large, very connected areas of green space that allow animals to move around or animal subpopulations to interbreed and have access to other parts of the habitat. This is very important for organism health. However, you can have quite a bit of human development in an area and still maintain large tracts because up to a certain point you're going to get connectivity between all of these green spaces that are there. And this is the middle diagram. There's still a large amount of connectivity. In particular, there's one patch that goes all the way from the bottom left to the top. And these are large patches, and there's very few isolated patches of 1 or 2 squares in this diagram. But if you reach a critical ratio of, in this case, human development, a critical ratio of blocking parts of the habitat, you end up with fragmentation, which is when you leave little spots just out on their own, or the habitat patches that are there are just not big enough to support a population. And like I said before, it's not just the big animals that need room to roam and need room to find their next prey or diversity of food, but even something like a frog, if something happens to its little pond and it's totally isolated, it's just out of luck. It can't just jump over to another pond. That's the problem with fragmentation. Or over a period of time, the genetics of a population that's too isolated maybe become unhealthy because they aren't interbreeding across a larger population. Now, there are other spatial grid examples that you can see in the reading and in the videos and in the simulations. That is, besides habitat fragmentation, one is forest fires. You're going to deal with this in the simulations. And there's a critical density that causes them to spread. But focusing a little bit more nuanced view of this, there's processes that continually lead to a changing mosaic. Little intermediate disturbances that hit just part of the landscape open up a new area. This might be caused by wind blowdown, landslides, small floods, lightning strikes. All of those open up a new area, and this allows for those continual small patches to go through the process of succession. And succession is when you have, say, bare land coming up with grasses to shrubs back up to trees. That process means that as there's all different age groups of succession going on. There's also all those different plants which supply different resources to the animals and broadly insects all the way through mammals to this larger landscape. So this leads to higher biodiversity across the whole landscape area that has these little patches in it. And we're going to see a very similar approach, that is using this network approach, when we have reserves or parks or green spaces and trying to artificially connect them with human-made corridors to increase the effective size of the patches that we do have. Okay, now the insights from this approach, using a network to look at these problems. One is that intermediate connectedness is good. We saw that with food webs, that that everything isn't connected to everything else, and so there's some compensatory response that is distributed out through the network. On the landscape, we saw the intermediate disturbance hypothesis in this mosaic. And this is very similar to what people have described in sociology and business. Granovetter described how connectors, that is certain people that move between networks, really increase the value of the overall system by moving ideas or moving resistance to disease across these networks. And more recently, in a more business approach, Bert has described brokerage and closure. Again, closure is when you have an isolated little company, and brokerage is when you bring in ideas from other areas. So that's one way to describe the intermediate connectedness. The other was just sort of a Goldilocks, that poorly connected or underconnected networks, that little pieces act as individuals of small networks with very little options, and overconnected networks just act as one unit that all behaves the same, and so it doesn't have the dynamics of a intermediate connected network. Now I want to apply this to a tougher problem, and the point of this is not for you to learn about my research in algae and Upper Clem Lake, but to show you how to use this network tool as both a heuristic and a way to discuss and engage discussion. So that original diagram on the front page, it's here, and this is something I generated in a software called Gephi, which identifies all the possible connections and the nodes, well, not all the possible, but the ones I could put in. And I'm going to show you how to use this as a heuristic tool and for broader discussion. But just looking at this diagram, in the sort of blue are a couple of the major players, which is DO, stands for dissolved oxygen. AFA is the name of the algae that I focus on, and we either have AFA respiration or AFA photosynthesis. PAR stands for photosynthetic active radiation. And this gets to be sort of, these shorthands here are really important, because otherwise I couldn't put all those in the little node and make a diagram out of it. The whole page would be just filled with words. So in the sort of lingo within my research group, this would all make sense to them. And then if I was talking to a broader population, I'd either have to go through each of those or make a bigger diagram that had the words spelled out. But in any case, this network diagram shows all of the sort of things that we're considering are important in controlling algal blooms in the lake. Now, one way we can use this diagram is to focus in on one little aspect. And in this case, I've taken the overall diagram, I translated SVG editor, which again are open source, widely available, and I've highlighted a few of the arrows. And in this case, there's two little network loops that I want to discuss. One is this photosynthetic active radiation to algal density to turbidity. And when you have high turbidity, it blocks the light, which allows the algae to grow just at the surface. And the other loop is when you have photosynthetically active radiation, has to go all the way to the bottom of the lake, which we're talking about shallow lakes, so that's 3 or 4 feet, and that allows the plants to grow from the bottom, which dampens the mixing strength in the water, which decreases the turbidity, and turbidity is like the amount of mud in the water, and increases the amount of photosynthetic active radiation that feeds the plants. And this is a common thing we see in these shallow lakes, which is a multi-stable state between algae that just grow at the surface in high turbidity waters, or clearer waters that have emergent plants. And so right in the diagram, we need to acknowledge that we were capturing this multi-stable state aspect of Upper Klamath Lake. Another way is in the discussion, we can have a group discussion, and if somebody makes a point in Gephi, just while it's being projected, you can click on the little thing, like here I double click over on marsh plants, it would pull up a little window and I can annotate it. And I can say, oh, here's an example that here we've got marsh plants and what's happening with that. Well, the marsh flow will contribute to the humics of the lake, and the input might be seasonal. We can put those comments right in, so it's a way to capture information from a diverse group. Somebody might have whatever comment they want to make. We can just add right in. Okay, another part would be to highlight some of the factors. And while you're, again, running Gephi, and I'm sure it's the same for other software, as you mouse over a particular node, it shows the other nodes that are one link away from that. That's very, very useful. So in this case, if I moused over the algal density, it would show all of the links that are just right next to it. Buoyancy, Daphnia population, currents, turbidity, photosynthetic active radiation. So it's a way to highlight those, and we could use that in an active mode to say what linkages have we put into this diagram, and which ones are we missing? Should we make some other linkages? So it's a very flexible tool to have that discussion. All right. Finally, I want to talk about the relationship of network to other approaches. Now, when we talked about patterns, we focused on how they're very descriptive, and we can use these network diagrams as being very descriptive. However, in patterns, there was no general rules that relate to ecology, whereas in networks, there are, such as intermediate connectedness being good, or there's some things about networks that really do apply to ecological networks. The network approach can also be used to visualize the patterns of relationships, and a grid network simulation, like we see in forest fires or the habitat fragmentation, essentially produces a pattern, a visual pattern that we need to interpret, like the mosaic. Now, stock and flow systems are much more constrained in what happens in the description, which, again, the strength was, and that allowed us to apply what we abstract from a stock and flow system to other stock and flow systems. But node and arrow diagrams and stock and flow diagrams are very similar. So for example, if we're studying a food web, we could have a node and arrow diagram and a stock and flow diagram. They're very similar how they look. It allows us to have that sort of homology between the problems. That allows us to compare what does a stock and flow system tell us that's different from a network approach, and really focus on that comparison rather than have a whole different representation for each system. However, network descriptions are much better to talk about resiliency. And resiliency, again, is this compensatory response of the networks that makes them healthy and be able to withstand a large amount of stress. And that just comes through a lot better in the network description, because so much of resiliency depends on the interrelationships between organisms, and it's not totally dependent on the stock and flow type energy and material relationship. So that's a much better way to talk about resiliencies with network language than strict stock and flow. Finally, I just want to tell you, if they are using these sorts of approaches in your other studies, what you can do. So these tools are available, and you can extend your use of them in more rigorous and sophisticated ways. So for example, if you want to do pattern analysis, you can use statistical software and simulations. And for example, we use R, software R. For dynamic simulations of stock and flow diagrams, the ones that I've shown in class were the visuals were created in Stella, and the simulations that you are getting at in the course were generated with Stella. And finally, for network relationships, I showed you Gephi, which is a nice piece of software that once you learn how to work with it, you can capture and represent a lot of these network relationships.